type questions. Either one is fine. Yeah, sure. From the test. Okay, number 6. So lab exam 1, number 6. So this is one where it describes the motion, and you have to draw a position versus time graph for it. So it says at time equals 0, the object is at 0 position, so p equals 0, and it's moving in the negative direction. So I'll write that as the velocity is negative. Then from there, the object speeds up. So what does that mean if the object's speeding up? What does that tell us about the acceleration sign, and how do we know that? That's right. If it's speeding up, velocity and acceleration have the same sign. So acceleration has to be negative. And then slows down until it's at rest. So how do we interpret that it slows down until rest? Well, it's still moving in the negative direction. So if it's slowing down, we have to have a positive acceleration. So acceleration is positive until, what does the graph look like if it's at rest, once it's at rest? It'll be, it doesn't say anything about how long it stays there, but we know that the tangent has to be horizontal. The slope has to be 0. So it's going to be a positive acceleration until it's horizontal. And then it speeds up in the positive direction. Okay, so if it starts at rest and then speeds up in the positive direction, what's the acceleration going to be? What's the sign of the acceleration going to be? Well, if it's at rest, then whichever way it accelerates, it's going to be speeding up because you can't get any slower than stop. So that's going to be a positive acceleration to speed up in the positive direction. Okay, so let's draw this. So it says that at time equals 0, the position is 0, and the velocity is negative. So it's going to be at 0 position, and it's going to have a negative slope at that instant. And from there, we figured out that the acceleration has to be negative. What do we know about the shape if it has a negative acceleration? Concave down, yep. So it's going to start like this and then be concave down. Then it slows down from there. That tells us that now the acceleration has to be positive until it's horizontal. So it's going to be concave up until it's horizontal. Okay, so now that's at rest. And then it's going to speed up in the positive direction, which means it's going to be, the acceleration is going to be positive from there. So something like that. So yeah, if you can figure out a way to just make it sort of systematic about, like, how do you use what you know about the velocity? How do you use what you know about the acceleration? That's what you really want. Any other questions about that one? Any other questions about the test? Yes, Lydia. Okay, so 5. I'm just gonna I'm gonna do like the short version of number 5 and any problem that asks similar stuff to this. So 5 looks something like this, and it asks you a bunch of stuff. Where's the acceleration positive? Where's it speeding up or slowing down? That kind of stuff. So I would mark the endpoints. And now I would go through and mark all the places where the velocity changes signs. That's all the places where the tangent is horizontal. So that's going to be here, here, and here. And then I would go through again and mark all the places where the concavity changes from up to down or vice versa. So it's concave down all the way from here, somewhere in here, right? You know, but it's concave down until about there. Now it's concave up from there. So I'm going to mark it like that. And then it's concave up from this point until somewhere in here. So I'm going to mark another one there. And then label these. So I'll call it A, B, C, D, Gary, E, and F. You can call it whatever you want, is all I'm saying. Okay, so turn that off. This is my show. And now you have all these different sections, and in each one of those, just figure out what's the sign of the velocity and what's the sign of the acceleration. If you've gone through and done it like this, then you're going to have the same velocity and the same acceleration sign in each one of these intervals. You've broken it up into every place that those can change. Okay, so from A to B, velocity is positive, acceleration is negative. From B to C, velocity is negative, acceleration negative. C to D, velocity negative, acceleration positive. D to Gary, velocity positive, acceleration positive. Gary to E, velocity positive, acceleration negative. E to F, velocity negative, acceleration negative. What I would recommend doing is on problems like this is just do that before you even look at what the questions are. Now you can just sort of read the answers off of it. So where is it slowing down? Anywhere where velocity and acceleration have opposite signs. So it's slowing down here, here, and here. Positive acceleration, if it asks that, it's here and here. Negative velocity is, so negative velocity, negative velocity, negative velocity. I think that's the easiest, sort of most efficient way to do those. Any other questions about this test? Yes. Mm-hmm. Mm-hmm. Okay, yeah. So this is distributions. So this is from the lab, not one of the tests, right? From the distributions lab. Okay. Oh, okay. Okay, number 3. It says that the average value is 9.68 and the standard deviation is 0.50. And so like for C, how many values are within half a standard deviation, so I'll call it 0.5s of the mean. 0.5s is half of that standard deviation, so that's 0.25. And so the range is 9.68 minus 0.25 to 9.68 plus 0.25. And so this is 9.43, and this one is 9.93. So now we're looking for just all the values that fall. So there's 15 total values. If you look through them one by one, 5 of them fall within this range. So 5 of them are between 9.43 and 9.93. And so the percentage within half a standard deviation is just 5 over 15 times 100%, so 33%. For a normal distribution, you would just read off all the percents. So go to that normal curve, read off all the percents between negative 0.5 and positive 0.5. So that's 19.1 plus 19.1, so 38.2%. And so the value we had was pretty close, especially for such a small experiment. If you just look on the, after number 7, there's a graph of the normal distribution. And so just read those percentages. We want everything between negative 0.5 and positive 0.5, and just read all the percentages in between. For one standard deviation, you'd add up all the percentages between negative 1 and 1. You get 68.2. Any other questions? Yes. You're next. I think that was 0.05. So number 1, I think it was 0.05 and 1.37. And then number 2 was negative 3.06 and 1.29. Mariah? Yeah. Okay. 5D. Okay, so speeding up are all the ones where velocity and acceleration have the same sign. So it'd be this, this, this. And the other way you can think about it, it's always nice to have more than one way to think about, to approach a question, because you can sort of check your results one with against the other one. Make sure you're not making any dumb mistakes. So it's also speeding up if it's going from closer to horizontal to farther from horizontal. You know, if it's starting closer to horizontal and finishing farther from horizontal. So from B to C, the slope slope up there is exactly horizontal. And then it's getting steeper from there. It's getting more negative from there. So it has to be speeding up in the negative direction.
I guess I'm really
Yeah.
confused on
Okay.
like I'm having a hard time like reading it.
Okay.
Like figuring out like why is acceleration negative?
Okay.
B,
Yeah.
but then it's positive.
Okay.
Why?
Right. Okay. So let me just do this again. Well, let's see. Let me just blow it up a little bit. All right, so the sign of the velocity is determined by the slope. And the sign of the acceleration is determined by whether it's a cup or a, what did I say? A cup or a frown. Cup or a frown. Yeah. So and for it to be a okay, so if you only look at this part from here to here, okay, that's like a really nice cup, right? Like what is it about the curvature there that
Like I can read velocity, I just can't see it.
velocity, you have, yeah, acceleration, yeah. So in order to make, so you have a frown shape and a cup shape, right? And we're just sort of trying to figure out how you know when it goes from one to the other one. Another way to think, see if this might help for some, this might help for you, some people, instead to think about it as like, think of a succession of slopes, okay? Are those slopes becoming more positive or more negative? That's what it's sort of really about mathematically, you know? Yes. Yes.
The way I have it as soon as I'm taking out
Mm-hmm. Mm-hmm.
in order not to hit the ground, that's kind of the way how I acceleration.
Mm-hmm. Uh-huh.
What kind of acceleration?
Yeah. Uh-huh.
Oh, because then in the middle, like if you go
Yeah.
that kind of makes sense because then but then why is acceleration going up if you're not even falling down the ground?
Let me finish the thought. Yeah.
Accelerate positively, but you just barely not hit the ground when you start. And then, so like from B to C, you're speeding up as you're going fast, but you have to start slowing down every
Uh-huh.
so the velocity and acceleration.
Yeah, so yes. And so tell me, I think this is sort of what like related to that way of thinking about it. So one thing you can do is think about so one thing you can do, the way I did it the first time, is I said, you know that like between B and C the velocity is negative. And I said, to me, I know that the acceleration is negative because it's concave down. And then from there you can tell whether it's speeding up or slowing down. But you could also say, okay, from B to C, the velocity is negative, and it's getting farther from horizontal, so it's speeding up. You know what I mean? It's from B to C, the slopes are getting farther from horizontal. And so if instead you know that the velocity is negative and it's speeding up, then the acceleration has to be negative also because velocity and acceleration have to be the same sign. That didn't help.
No, yeah, that actually
Okay.
really did help.
Okay, so you can, so those are two different, like basically in either case, you know two of the things and you use them to figure out the third thing. And whichever two of those are easier for you to visualize, you can do those two and use them to figure out the third one. Okay, sure. Yes.
I just wanted to say, like how I see it is how it's visually drawn. So like from B to C, it's half of the concave,
Mhm.
and concave is negative acceleration. Whereas from C to D, that's you're getting into halfway through the
Mhm.
through the cup. So you're already in the cup.
Mhm.
So that's positive,
Mhm.
I guess. Because towards the end of C to D, it's going into a cup shape. So then it's
Yeah.
Okay, yes. Yes, thank you. Anybody have any other questions about this? All right. So now we're getting back into, we were talking about, so it actually, we went back to 2D kinematics on Wednesday, but on Monday, we started talking about 2D kinetics. And the big result from 2D kinetics is Newton's second law. And Newton's second law says that if you add up all the forces on the object, and that idea of choosing an object, being very clear to yourself about what the object is that you're analyzing is going to be important. F net is equal to the mass of that chosen object times the acceleration of the chosen object. And the thing that sort of subtle fact that you have to be careful about with this, it's not going to be too important for us early on because we're not going to have like rotating objects or whatever. But if you have an object that's rotating, different points on the body have different accelerations. Okay, so that is a pain. But that means that this can't represent every single point on an object. It only can represent one. And so that's the center of mass. So this is always the center of mass of the object. And to be clear to ourselves, about, let me say it like this, be clear about the boundary between our chosen object and the surroundings we're going to draw a free body diagram for every time that we use Newton's second law. Free body diagram. Every time we use Newton's second law. And so if you use Newton's second law without a free body diagram, in this class, I'm going to take off a small number of points, but just to make sure that you get in this habit. The thing about free body diagrams is like, it's sort of too bad that it works this way. Like at first, often people don't really see the benefit in drawing free body diagrams, because we start out with the simplest problems. And the simplest problems, you can do this kind of stuff in your head without too much trouble. But when you get into more complicated problems, these are really useful. And well, you don't see that for a while. And the danger is that you get in the bad habit and then you see the hard stuff and you don't really know how to approach it. We're going to try to be very careful about getting good habits. And then when we get to the harder stuff, it'll be done. So, okay, free body diagrams. I'm going to abbreviate these FBD. And like I just said above, draw a free body diagram every time you use the consent law. Okay, so here are the steps for drawing a free body diagram. The first one is to draw a closed outline of the chosen object with no internal details and no outside objects. Okay, so for example, we did a couple problems with this man on the scale. If the chosen object is the man, then the closed outline would look something like this. Not this, because it's not a closed outline. Not and I mean, I could have drawn it like a gingerbread man shape if to make the man feel better about his conditioning, but that has internal details, the facial features. So we don't want to do that. And not this one, because the scale and the ground are external to our chosen body, and we don't want that in there. Okay, so the name free body diagram free in free body diagram refers to the fact that we're drawing our object and it's free of anything else. Okay, and the outline is because we really don't care about what the object is. It sounds harsh, but we don't really care anything about this guy except what his boundary is. That's all we want. And so that closed outline makes it very clear, like anything outside the skin there is surroundings, anything inside is included. Second, step 2, draw a downward arrow from the middle of the chosen object. That's going to represent the weight force and label it with the object's weight. Or you can also label it mg. So for example, so here's the weight force. You can write it as, if the mass is 100 kilograms, you can write this as 981. Or if you don't know the mass, or you just don't want to calculate it yet, you can label it mg and come back and deal with it numerically later. But that just says that the force of gravity is pointing down, and it has a magnitude of that. And then 3, this is the last step. At each place where the surroundings contact the boundary, draw an arrow in the direction of the contact force. An arrow in, say it like this, draw an arrow in the direction of the force applied to the chosen object. And then label that arrow with a number or a variable. If you know the number, you can put it down. Usually these are the kind of things that we have to solve for. Okay, so in this example, we have the weight force of 981, and we're going to know in 10 minutes or something, we'll know that the scale is pushing up on the man's feet. And so the direction of the contact force applied to the man's feet by the scale is up. And then give it a variable name. I'm going to call it capital N, but we'll talk about that more in a little bit. You could call it X or Y or whatever. I'm going to call it capital N for normal force. So for the example of the man standing on the scale, this is a complete free body diagram. Okay, and if you're, usually our coordinate system is going to have the y-axis up. So this says we have a force of 981 newtons in the negative y direction and a force of N in the positive y direction. One thing I want you to notice about the free body diagram, the free body diagram gives the entire left side of Newton's second law. That's the F net side. Of Newton's second law. So if you do your free body diagram right, then you're just sort of reading those off to put them in the left side. It doesn't tell you anything about the acceleration. This free body diagram is the correct free body diagram where the scale is on the ground, or in the case where the scale is accelerating one way or another. And so you can't tell any difference, even though, you know, those accelerations change. But it tells you everything that goes into FNet. Yep. 981. Yeah. So like in the example, the last time I was drawing this picture, he had a mass of 100 kilograms. So that's 100 times 9.81. Okay, well, so that's it for the steps for drawing a free body diagram, except for now we don't know anything about the directions of contact forces. So now we just need to know something about the directions of different forces. We already have gravity, so these are all contact forces. Okay, so what are the different types of contact forces? Well, I'm going to break that up into first pushing contact along flat surfaces, along a flat surface. Pushing contact along a flat surface. Second, pulling contact. And one way to think about this, like how do you know if you have pulling contact? This is the case where the contact could be replaced by a cable, you know, a string or something. And then the third and last one is friction. So the difference between pushing and pulling, I think you can really answer the question of which one you have just by thinking of replacing the contact with a string. You know, if so, what about the contact between my hand and the table right now? Could I, like, if I put a little string in there, could I make that string apply the same force? No, because it would just crumple. You know, so that has to be pushing. Okay. If I'm doing this, could I replace that contact with a string? If it's strong enough, you could. You know, I could just as easily be holding on to the end of a string and pull the table up. Okay. So that's kind of the distinction. Then friction happens parallel to the surface. We'll talk about friction in a couple days. But friction only deals with things that are sliding along a surface. Yes. Not from where your hand is, though. So think of just wherever your hand is or whatever the thing is applying the force. Think of just moving your hand a little bit and putting a string in between you and you know what I mean? So if I'm underneath pushing up on the table, I couldn't put a little string there and have that string apply that force. And you could also think like, if you're applying that force with your hand, are you like blasting your triceps? Are you blasting your whatever, lats? Okay, so I'm going to start out with that pushing contact force, and we're just going to go through these different types one by one. So the first one, pushing contact along a flat surface. So whenever two objects are pushing on each other, and you can't have one pushing and one pulling, it doesn't work like that. So when two objects push against each other, the force applied to the chosen object is, so there are two things you have to remember. It's first perpendicular to the surface of contact. So when I say contact along a flat surface, this surface of contact is that flat surface. And second, toward the chosen object. And so then it also has to be away from the contacting body. Okay, so let me show a couple of examples. So first, let's think of two little carts rolling along a surface, and they're in contact over here. And let's say you're applying some known force F over here. And that force F would most likely be applied by something pushing here. Let's call the left one body 1 and the right one body 2. And I'm going to draw free body diagrams of, so I'm going to first draw a free body diagram as if we're isolating body 1. Then I'm going to draw a free body diagram as if we're isolating body 2, and we'll see what the differences are. So what are the contacts? What are the pushing contacts along flat surfaces? There's this one between 1 and 2. And there's this one between the wheels and the ground. And there's this one between the other wheels and the ground. So in this setup, there are 3 places where the things are pushing on each other. And if you want to make sure to yourself that those are all pushing, imagine moving each one of these cases, putting a string in there, and just see whether the string tightens or compresses. You know, if it compresses, it's pushing. If it tightens, it's pulling. Okay, so first, free body diagram of the first one. So free body diagram of cart 1. So I'm going to draw an outline of part 1 with no internal details. You could just draw a box, but I'll put a little extra detail in. You can't see anything from cart 2 because that's surroundings, and we want cart 1 to be free of the surroundings. And so there's a downward force. I didn't say anything about the masses, so I'll just call this mg, or I'll call it m1g. The other one is going to be m2g. And now I'm going to go around the boundary, just mentally go around the boundary of the object, looking for places where the surroundings make contact with the boundary. There's definitely force over here, so I'll put this in. And if I keep going counterclockwise, the next place I get to is the wheels. I'm going to lump the wheels together as a single thing just because all of the objects that we are dealing with now are particles. So there's not really separate, I'm going to just treat it like the ground and the wheels make contact at a single point. Okay, well, it's pushing contact. The surface of contact is the ground. And so the pushing force has to be perpendicular to the ground. So either up or down. And the way you choose whether it's up or down is it has to be toward the chosen object, away from the contacting object. So it's up or down, and then it's toward the wheel, away from the ground, so up. And I'll call this N1. That capital N stands for normal force, and normal means perpendicular, so it kind of makes sense probably why you would call that a normal force, but I'll talk about it in more detail later. And now keep going around until you find the next place where the boundary is in contact with the surroundings. Where's that? Where it touches 2. Surface of contact is vertical, and so the force has to be either to the left or the right. We want it toward body 1, away from body 2, so it has to be to the left. And I'll call this capital R for reaction force. That's just what pushing forces do. If you want to make sense out of that, I think you can think about what direction stuff goes when you push on something. Like if you push on my shirt goes toward me. And so I'm not sure if I have a better description than that. But yeah, if you just imagine that the boundary is soft or whatever, which way does the boundary go when you apply that pushing force? That's the direction that the force acts. Yep. The F? That force F, yeah. So yeah, those both have to be in there. Yeah, R is coming from what did I call those? Cart 2. So we have, and now we're done. There are no other places where the surroundings make contact with the boundary. So this is a complete free-body diagram. So we have the force F. We don't know where that's from. We're just given that that's being applied. We have the normal force pushing up, the weight force, and the force from cart 2 pushing that way. And then if you wanted to turn that into the net force vector, this is in the positive x direction, positive y direction, negative y direction, negative x direction, and you can make those all vectors and just add them together. So now I'm going to do a free body diagram of cart 2. So there's the boundary. steps for the free body diagram. We have the boundary, no internal stuff, no surroundings. Put the downward force representing the weight. So that's the mass of car 2, M2, times 9.81. And I'll start again down at the bottom, going around the boundary. There's a pushing contact between the ground and the wheels. That's perpendicular to the ground, toward the wheels, away from the ground. So it has to be this way. So I'll call that N2. And then there's nothing as you go around until you get to the left side. That's another contact force. The surface is vertical, so it has to be to the left or the right. And it's toward cart 2, away from cart 1, so it has to be this way. And label that with a variable. I'm going to call it R. One thing I just want to be, so that's right. Okay, so that's something for later, you know. It turns out that when two objects are in contact, the magnitude of the contact force is always the same. We'll talk about that more in depth later on. So for now, you don't have to worry about that, but we will see that this R is always the same magnitude as the other one, just different directions. Anybody have any questions about these?
So would there still be an F force on the other one going the same way?
Yeah, you'd think so, because this cart 2, if you apply this force, they're both going to move, right? And this one isn't going to move if there's no F.
And if the R's are the same, you can't, you know what I mean? Like you couldn't put F into R and then have that R be the same as that R.
Yeah,
No.
you would think. But no, so the way to do this is apply the weight force, go only around the boundary of your chosen object and apply those forces. Don't apply any forces that aren't right on the boundary. So this F really should not go here. Okay. That seems weird,
Yeah.
but the way it's going to work out is what that F really does. I mean, that F doesn't move that cart. What it does is it makes this cart try to move, which increases this contact force R, and that contact force is what moves this. Okay.
So it increases both R's.
Yeah. If you think of R as one thing, it's just acting in two different directions. Yeah. So yeah, F does not act on 2. 2 doesn't feel that force F, except indirectly through the contact forces. Any other questions about that? That's going to be a weird thing to get used to, but the easiest way to do it right is just to be really disciplined about saying, so I draw my free body, now I put in the weight force, and now I just go around the boundary and nothing else goes in, you know? Okay, let me do an example problem. it's going to look just like that one. Okay, so let's say this is 10 kilograms. And it's in contact with the one next to it, which is 20 kilograms. And let's say, well, I guess I have this going the other direction. There's a 30 Newton force over here. And we want to do two things. First, what's the acceleration vector of the pair of carts? They're both going to have the same acceleration. And then second, what's the force vector applied to the 10 kilogram cart by the 20 kilogram cart? And actually, this is, let's see how this works. So let's do a third one. What's the force vector applied to the 20 kilogram cart by the 10 kilogram cart? Okay, first for part A, we're going to, so our chosen object is going to be the pair of carts together. There's nothing that says you can only lump one thing into your chosen object. I mean, if you think about it, like everything we think of as an object is really made up of whatever atoms and stuff, you know. So it's perfectly fine to, you know, our chosen object is going to be both lumped together. And we're going to use Newton's second law, so we have to start with a free body diagram. So that looks like this. Again, you don't have to do it with all this detail, but I'm just trying to make it clear what we're looking at. Okay, so draw an arrow down from the center, representing the weight. Mostly just to show how awesome my computer is. Okay, so first thing is the weight. The magnitude is going to be the mass of our chosen object times 9.81. What's the mass of our chosen object? Yep, 30. So 30 times 9.81 is 294.3 newtons down. And now I'm going to go around the boundary looking for contact with the surroundings. First, there's this applied force of 30 newtons over here. That's applied right to the boundary, so it's included. and then keep going counterclockwise. There's nothing until you get to the ground. And I guess I'll just lump this into a single contact force between the ground and all four of those wheels that I drew. So I'll just call that N. Okay, so that's everything in this free body diagram. There's no boundary between these two parts. We have them lumped totally together, so there's no force. I mean, there are forces between them, but we just don't have to worry about them because the way we've isolated this, there's no boundary. So that's everything that goes into the net force. So Newton's second law. Let's write these as vectors. If our coordinate system has the y-axis up and the x-axis horizontal, how do you represent that vector n, that force vector with a magnitude of n as components? Yep, it's in the positive y direction, so that's 0 n. How about the weight force? Zero, and that's in the negative y direction, so 0, negative 294.3. And then the 30 Newton force is in the negative x direction, so that's negative 30, 0. And so this is F net. And then that's equal to the mass of the chosen object. What was that again? 30 times the acceleration. And now this is something we're going to use a lot in problems where things are rolling or sliding. We're going to assume that we don't know what direction it's going to go, but we're going to assume that we know that it's not going to jump up off of the surface, sink down into the surface. Okay. So we're just going to say we know from imagining the allowable motions here that all the acceleration is going to be in the x direction. You know, it could be positive x or negative x, but I mean, it's all horizontal. Okay. Yes? Because that's in the negative x direction. Yes? Newtons. Yep. Everything in the free body diagram is a force, so they'd all be Newtons if you're doing SI units. Okay, so we're going to make the assumption that the acceleration can be written as some value a. It has an x component and a 0 y component. It's not sinking into the ground or jumping off the ground. So this represents, you know, only horizontal motion. Which one? The 30 on the right side? This is saying F net is equal to mass times acceleration. So this 30 and this 30 are different. But this is the mass of 30 that you get from adding up the two individual masses. Ooh, that'll be interesting to read later. Just kidding. I mean, it might be. Okay, so now we have an x and a y equation. We can break it up into two different. So the x equation says 0 plus 0 minus 30 is equal to 30a. And the y equation says n plus negative 294.3 plus 0 is equal to 30 times 0, so 0. We're trying to get the acceleration vector. So what we really want is that value a. This here all together, the acceleration vector. We just didn't know what that variable a was yet. So this one, negative 30 is equal to 30a. Divide both sides by 30, and you get a is equal to negative 1. Well, we're just going to call it a. I mean, you could call it ax. That's just a different variable name. I think you're thinking about it right. But I mean, since there's no y component, we'll just call the x component something simple. And so from this, we know that. So now take that value of the variable a, plug it back into this thing in the dotted line, and the acceleration vector is equal to negative 1, 0 meters per second squared. Or in other words, in the negative x direction with a magnitude of 1 meter per second squared. Any questions about that? Okay, so the next thing we want to do is figure out the contact forces. The force, so the first one we're asked for is what's the force applied to the 10 kilogram cart by the 20? So now the chosen object is going to be the 10 kilogram cart. So I'll draw a free body diagram. There's the outline. There's a weight force acting down of, this has a mass of 10 kilograms, so that's 10 times 9.81, 98.1 newtons. There's a force pushing up from the ground. I'll call that N10. That's the normal force on the 10. Not really going to come into this. Then you get over to the right side, and there's contact from the 20 kilogram. And it's a pushing contact along a flat surface, so it points perpendicular to that vertical line toward the 10 kilogram, away from the 20 kilogram. And we don't know what the magnitude is. And now there's nowhere else where there's any contact with this body. Yes? That's what that R is. But we don't know anything about how big that force is. I mean, so what you're saying is basically like, we're not really going to use the fact that it's 20 kilograms. You could write that as a description. That force R is the force applied by the 20 kilogram cart, but we can't use the mass for anything. All we know is that it's pushing, so we know the direction. Any other questions about that? Yeah. It comes into it just through Newton's second law. So, I mean, I think the way to think about it is like, just be systematic about drawing the free body diagram, putting the stuff in Newton's second law. And if you put everything in the right place, all the numbers come out, you know. Yes. Yes, that's right. They are going to be. And actually, we're not going to do it today, but next class, I'll do the same calculation for the other one, and we'll see that you calculate the same R. And that just always has to be the case. That's Newton's third law, equal and opposite reactions. Okay, so these three add up to the net force. So Newton's second law says N10 is in the positive y direction, so that's 0, N10. The weight force is in the negative y direction, so that's 0, negative 98.1. That force R is in the negative x direction, so that's negative R, 0. And all that's equal to the mass of our chosen object. This time it's only 10. Times the acceleration vector of our chosen object, which, if you think about it, these things are moving as a single unit. So the acceleration vector that we calculated in part A, we can use here. Okay? So this is negative 1, 0. So we calculated this acceleration vector in part A. And now we have two equations. The x equation says 0 plus 0 minus r is equal to negative 10. And the y equation says n10 minus 98.1 plus 0 is equal to 0. So the x equation says r is equal to 10. This here is the force on the 10 by the 20. We just didn't know what r was yet. So now we can plug the 10 that we calculated in for r, and we get that the force vector, I'll write it like this, on 10 by the 20 is equal to negative 10, 0 newtons. Or another way to write that, it has a magnitude of 10 acting in the negative x direction. So 10 newtons that way. So what do you think the force vector is going to be? We'll calculate this next time. The force vector on the 20 by the 10. That's right. It's going to be positive 10, 0. The exact opposite direction and the same magnitude. Yes? Mm-hmm. In this case, it is, but not always. If you have a rolling or sliding problem where where that normal force is the only other force besides gravity and the surface is horizontal, then yes, that'll be the case. But I think the best approach is just to calculate it each time because there's so many cases that can get messed up. Eventually, you'll just, like if you do a million problems, you won't do a million in this class, but if you end up going into another class and whatever, eventually you get sort of a feel for it, but it just takes repetition, you know. Okay, that's all. Let's do the lab exam in here. Okay, so meet in here for the lab exam. The people are taking it tonight at 7:30.